Dielectric spectroscopy and dielectric mixtures. How do existing models for binary and ternary mixture models for insulation design compare? The layout for this podcast includes an introduction, method, results, discussion, and a conclusion. Introduction. In the following diagram, the pole-mounted insulator is used as a support for the conductor so that it can continue carrying current along the pole via the conductor and have no current flowing through the pole. Dielectrics are defined as materials in which the primary charges in the atoms and molecules are bound charges held in place by atomic and molecular forces. A dielectric binary mixture is defined as a material consisting of two constituents with low electrical conduction. Problem statement. This project investigates the dielectric properties of a dielectric binary mixture, specifically ethylene propylene rubber (EPR) and porcelain. They are both used as pole-mounted insulator for single-phase voltage lines at 12 kV, subjected to frequencies between 57 Hz and 62 Hz. The dielectric properties under investigation are the conductivity, also known as the leakage current, the permittivity, and the electric field strength.
For our methods in our project, we use analytical methods as well as simulations and COMSOL. The analytical methods are used to determine the material properties. In mixing the materials, we followed the Laird, Maxwell, and Bruggeman equations outlined in papers research. Now, here shows the Laird method for mixing materials to produce a resultant binary mixture. The volume in this formula is relative to the permittivity of material 2. If we use a 50-50 mixture, then the formula becomes as shown in the third bullet, and this is very important as it shows that the two materials, material 1 and material 2, are interchangeable in this model. Now if we move on to do the Maxwell, again the volume represents the volume of material 2 in the mixture, and the materials are not interchangeable as they will produce different results if they are. Now the model also requires that one be modeled as a host, one be modeled as a filler. So we modeled porcelain as a host, EPR as a filler, and obtained a permittivity of 3.43. When we modeled EPR as a host, porcelain as a filler, we obtained a permittivity of 3.2. And the dielectric constant here shows that the porcelain as a host and EPR as a filler will produce better results. So we kept that model in the Bruggeman, which then produced 3.65 relative permittivity. In console simulations, we use two models, one model for the dielectric field strength and one model for the current through the dielectric. Here shows the setup for the dielectric field strength as well as the permittivity. We see a big cylinder here just with air inside, and then a small cylinder in the center which is our dielectric material. We see a plate on top of that. That's a copper plate to represent the power cable, and that has a terminal voltage of 12 kV. At the bottom of the dielectric, it is grounded. Then we went on to set up the circuit to determine the current through the dielectric, and here the voltage is 60 Hz, 12 kV, and the plates of the capacitor here are copper plates, and the resistance here shows the resistance of ground, which is basically resistance to the pole. Results and discussion. This is an example of one of the dielectric field plots obtained. All three materials in the simulation gave an average of 5.423 by 10 to the 5 volts per meter for electric field strength and had small deviations among them. This implies that the material can withstand a high electric potential before breakdown occurs, which makes it very suitable for our high voltage application. The graph seen here is a leakage current plot. Now, the graph shows that the current through the dielectric material is zero, and this can be attributed to the relatively small conductivity of the material that was calculated and inputted into the material properties, which essentially makes the conductivity of the material zero. Here we see the variation of frequency against the permittivities of the material, and we also see that the imaginary part is zero, therefore we don't expect any variation between permittivity and frequency, and we know that the imaginary part is zero again due to sigma being calculated as relatively zero.
In closing, we modeled a binary mixture using the following three mixture methods: the Bruggeman, the Maxwell, and the Laird. This was then used to calculate the effective permittivities of the individual mixtures. These values were then placed in COMSOL using a 3D capacitor model, which we obtained in COMSOL's documentation. The dielectric field strength was then plotted for the three mixtures, and almost identical results were seen for all of them. The leakage current was then simulated, and this gave virtually zero leakage current for all three mixture models. Upon investigating how complex permittivity varies with frequency, it was observed that this remained constant, which was expected since the range of frequencies for our application, AC power, is between 57 to 62 Hz. In closing, the results obtained for the binary mixtures were useful. However, one thing we were not able to investigate in COMSOL was the limits to the dielectric breakdown strength of the binary mixtures.